So anyway, we have no time for questions, so we can go to the next speaker. Thank you.
Okay, so I will follow up a bit on Daniel's talk and present a study which is motivated by Peter Jenniskens' Atlas of Meteor Showers. So we made a reanalysis of this new radar database that Daniel showed. And one of the things that was discovered was a new meteor shower, which is now called the January ZETA-LEONIDS. And as you see here, of course, there should be a reference to where the data comes from, and this will be in the IMC proceedings, and we will provide the data in an open source library so that it can be used for other purposes. But just quickly, with Daniel and I, and also Gabriel Borderes-Motta, who is here, we come from very north of Sweden in Kiruna. We don't have snow yet, but very soon, in 1 month from now, our institute will look like this. And we are a governmental research institute under the Swedish Ministry of Education, and we do a lot of different geophysical observations. Meteors are not part of our governmental mission yet, but we want to get it to become that. So one of the problems of observing meteors at our location, one could say, is that we are right underneath the statistical auroral oval. That means that we have aurora every second night. And we also have another set of nice phenomena. We have in summertime, we have the noctilucent clouds. We don't see them ourselves because we have midnight sun, but if you go a little bit south, you see them above our location. And in wintertime, we have the polar stratospheric clouds, which are signs of ozone destruction. And there's a lot of different instruments here. Gabriel will tomorrow talk about fireball observations with our auroral cameras, which is a bit challenging to use for that purpose. We have actually the access, we are scientifically responsible for meteor radar at the S-range rocket range nearby, which we hope to upgrade in the future as part of our mission. And as I mentioned, we have our basis in what's called the Kiruna Atmospheric and Geophysical Observatory, which is long-term observations of different geophysical parameters and atmospheric parameters. And of course, we would like meteors to be part of that. But today I will talk about then as data which come from the new radar, which was introduced in the previous talk. And just again, the data, they are head echoes. And we can then see quite much fainter meteors than visually, optically, and with specular meteor trail radars. And the example data where this January ZETA-LEONIDS were found came from a monthly campaign that we had in January 2014. So we were actually looking for the quadrantids, and well, there are other detections in this data. Each dot corresponds to one head echo, which is well characterized, and the color is the speed. So just in order to give some background on this meteor database, we performed some time ago now in 2009, 2010, a program where we had 24 hours of dedicated meteor observations each month. And as one can see in January, typically we see up to some 500 head echoes per hour in the morning, whereas in other times of the year, like in the autumnal equinox, we can see more. And the reason for these diurnal curves, these are not smoothed, these are just the data, the number of accepted meteors per hour, is because of what kind of source regions are above our local horizon. So with these head echo methods, typically we see meteors from the sporadic complex, and mainly the Earth apex meteors. So this is now a sun-centered ecliptic longitude and ecliptic latitude plot, and we have the apex of the Earth way in the center, and now it's zoomed into the apex, and we can see that during spring we don't even see the southern part of the Earth apex, and therefore we have lower amounts of detections. But if we now would combine these, taking into account the visibility above the local horizon, so then we actually see that the strength of the source regions in the long term, they are quite equal, both symmetrically north and south toroidal, and also helion and antihelion, and north and south apex on the long term. But we also see a lot of meteor showers. So the head echo data is very much comparable to optical data. but of course we can see things on the day side. So we have the helium source. And now this data was given to Peter Jenniskens, and we were analyzing it as part of this atlas. And of course, there are lots of showers in there, but as I mentioned, one of them is a new shower called the January ZETA-LEONIDS. And I could just mention that this the radar cross section, which corresponds to meteoroid mass of this, is a few tenths of square centimeters, which corresponds to about a sub-millimeter sized meteoroids. So 10 to the -8 kilogram particles. So they are not very, very large, and we could see about 1 per hour. So it's not very many, but during one night, during the campaign, we had 1 per hour from local time 9 in the evening to local time 9 in the morning as the source region passed the sky. And if I just show something from these are the kind of velocity profiles that we get for individual events. Now I don't show uncertainties here. These are just some central part of the distribution. And as Daniel showed earlier, we are now applying the new algorithm to these data, and then we can get radiant probability distributions for all individual events, which we think will be helpful in order to better characterize our data and also to look for showers. If we just look into one of those things, of course, it will actually the radiant will be connected with the initial velocity. So the solution sitting in this right ascension declination corresponds also to a higher initial velocity than the part over here, and this means that the orbital elements they are dependent quite much upon each other. They are not just round distributions. In our original database, we provided just uncertainties as Gaussian distributions, but this is of course far from the case. But if we look at one of them at a time, one element at a time, this is typically what we can see. So it looks fairly well sampled in this case. Okay, so I hope we are back on time again. So I would like to finish by this.
Well, thank you, Johan, for this quick and nice presentation. So any questions?
Okay, what's the meaning for J in JST for the timing?
Oh, that's the Japan standard time. So this was the new radar is located in Japan, and if we if we plot it in UT, it will be very confusing here because we want to look at the local time. So